Yeah, everyone, thanks for coming, and thanks for inviting me here as well. I'm going to be talking about a topic related to some of the talks we've seen today. And this is, of course, related to Mach's principle. But I've made the effort to try to distinguish this idea from this connection with gravity that we'll be discussing today. I'll go through a bit of background motivating what this is about, and then after that, I'll talk about a variety of different historical proposals that were proposed over the course of the 20th century for the unification of gravity and inertia. This is also in celebration this year of the 111th anniversary of Reissner's paper, which I think is the first time where this idea was expressed. And by coincidence, I think in a week and a half, I am turning 111 seasons old. So that's something I found out the other day. I didn't think, it turns out I'm going to be 333 months, which makes it 111 seasons. So there we go. Anyway, so let's get started. This is an outline of the contents of my talk. So the first will be some conceptual background on Mach's hypothesis, Mach's principle, what this means according to especially like how I'm going to explain it, because there's a lot of different accounts in the literature and so on. And then I'll introduce Reissner's hypothesis, why it matters, and then look at these different models proposed over the course of the 20th century, which to varying degrees involve this idea. Okay? All right. So first of all, Mach's hypothesis. So I call this thing Mach's hypothesis. Of course, most people refer to this as Mach's principle. But I'd like to make the effort to distinguish between these two, where principle has a connotation of something that sort of stands on its own feet, that that isn't really questionable, like the relativity principle, or like a principle that all measurement is a ratio of two things, something like that. So I'd prefer to call Mach's particular hypothesis about the origin of inertia hypothesis. But before that, what is it that motivates this kind of approach, this Mach's approach? In essence, Mach's principle is a critique of the classical conception of causation. Okay, this is what I argued in my paper from last year. And you can look especially at Mach's booklet on the conservation of energy from 1872 for this way of thinking. So in classical mechanics, causes are identified with forces which produce accelerations. But all of this system sort of necessitates that something define a body's motion in the absence of causes, right? If you say that forces produce accelerations, then an acceleration with respect to what is produced by a force, right? And in classical mechanics, in the absence of any forces, you still have motion defined, right? So, and in effect, when you're moving inertially, you can pretend like there are no causes acting on you, right? And so for Newton, the frame of reference which defines with respect to what inertial motion, so motion in the absence of causes, is defined, and therefore also allows you to define causes and forces and so on, is absolute space and absolute time. You need both to define velocity and so on. But for Mach, as for many others, space and time are only conceptual constructions, right? There only are ways of coordinating between things, real things. They're not real things themselves. And so we can't appeal to these as the framework for inertia. And moreover, nothing happens in the absence of causes, so there's this notion of inertial motion is flawed from the start. And so Mach suggests that the roughly homogeneous inertial motion we observe when, if you go into empty space and you throw an object forward and you observe it recede away from you at a constant speed, this evidence of inertial motion, this empirically, defined inertial motion, needs some cause, not in absolute space and time, which are inventions, but in some homogeneous feature of the environment. Okay? And he proposes, okay, before we get to that, so this essentially implies a modification of the Lagrangian in classical mechanics. If you take the Lagrangian, this is what defines inertial motion in classical mechanics. It's the kinetic energy. The v squared here is defined with respect to absolute space and time. Okay? And in the absence of that, you're going to have to modify the Lagrangian in some way, and we'll see how the models that we'll look at later on do this, in order to not have this reference to absolute space and time. Okay, but so what is this cause of inertial motion? Well, Mach's principle itself is agnostic about what the actual cause is, and in Mach's works you can find two different general classes of hypotheses. So if Mach's principle is the idea that inertia is required to have a physical origin, we can ask, what is it? The first one is that space is a physical medium causally responsible for inertia. And incidentally, this is what Lorentz believed. So this was one of Lorentz's arguments post-1905 for holding on to the existence of the ether, was that it was necessary to have the ether to define acceleration. Okay? But Mach also proposed another hypothesis, that physical space is really just an abbreviated reference to some relation to masses, to the masses of the universe, which are the real sources of inertial influences. And this is what Einstein aspired to do in his theory of general relativity. But he didn't really end up doing this, as we'll see. Okay. So the current paradigmatic theory of space-time and inertia, is it Machian? Well, it could be seen as Machian in the sense of the first hypothesis, right, where space is interpreted as a physical medium of some kind. However, it's a kind of hybrid between the first hypothesis of Mach and the second hypothesis, since it also includes inertial induction effects. So the properties of physical space in general relativity are affected by the motion and presence of matter. And so like frame dragging effects like the lens stirring effect have led some people to try to salvage Mach's principle within the context of GR and try to get the frame dragging in GR to fit to, getting a symmetry on the rotations of the universe. And Wheeler, for example, has tried to do this, among others. Okay, next. So Reissner's hypothesis. So, although Einstein did not produce a theory which successfully implements the second hypothesis of Mach, it was nonetheless crucial to Einstein's reasoning on his way to general relativity. And he referred to this hypothesis, Mach hypothesis 2, that I've called, as Mach's principle. I've argued this is a bit of a misnomer, it's a bit misleading. But Einstein's key contribution to this whole story, for our purposes, was the equivalence principle, of course, from 1907, which I think should also be called the equivalence hypothesis, right? There's no a priori reason why there should be equivalence between inertial and gravitational mass. So it's a hypothesis, it's a result that we observe, and that we hypothetically extend its generality beyond what we've observed so far, right? So this equivalence hypothesis comes from the observation that all objects fall with the same acceleration in a gravitational field. So the gravitational mass is proportional to the inertial mass. And just like So just like inertial forces, when you're in a rotating frame, for example, you have these inertial forces. Gravity acts universally on bodies, right? And this suggests the possibility of unifying gravity and inertia. And that's what I would say, Einstein's whole construction in the course of his development of GR involves considering accelerated observers and thinking that the acceleration of the observer generalizes the relativity principle, which it doesn't. But the true insight is that there's something in common between gravity and inertia, okay? All right. So if we combine this second hypothesis of Mach with the equivalence hypothesis, that gravity and inertia are the same in their very essence, and we can see that these two go together quite nicely, right? We know that inertial motion, so if Mach is right and inertial motion is conditioned by the masses of the cosmos, inertia comes from a mass-mass interaction. We also know that gravity involves a mass-mass interaction, right? Gravity is an interaction between masses. And so this already suggests the equivalence hypothesis, right? That gravity and inertia have something to do with each other. And this is what I'm going to call Reissner's hypothesis, is the convergence of these two ideas in the idea that by relativizing inertia, we're somehow automatically going to get gravity out as a side effect. Okay. Another way of thinking of this is that the properties of space which constrain motion in some local frame are due to an interaction with the other bodies, and this interaction is mediated through the force we call gravity. All right. So I think the first person to be thinking along these lines was, in fact, Emanuel Friedlander, and this precedes the formulation of Einstein's equivalence principle. And there's this short passage from this booklet. The citation is Friedlander and Friedlander because he writes it with his brother. So here's the quote. However, it seems to me that the correct form of the law of inertia, this is in the context of discussing the relativity of motion. So he's doing something very similar to Mach. In fact, he came up with the idea independently of Mach, and then his brother told him, well, actually, Mach's already formulated this idea before. But he adds, the correct form of the law of inertia will only then have been found when relative inertia, as an effect of masses on each other, and gravitation, which is also an effect of masses on each other, have been derived on the basis of a unified law. So this is the basic idea we're going to be talking about, this unification of gravity and inertia, deriving the two from the same single law. Okay. So why have I called this Reissner's hypothesis? I haven't mentioned Reissner yet. So in the second of two papers from 1914 and 1915, which treat this same issue, and the second paper is called On the Possibility of Deriving Gravity as a Direct Consequence of the Relativity of Inertia. Hans Reissner, for the first time, I think, in history, clearly articulates what I'm calling Reissner's hypothesis. First, this comes from like a critique of Einstein's equivalence principle approach to gravity. Concerning, so in the first paper, actually, he's criticizing Einstein's equivalence principle, and he sees nothing of use of it because Einstein was claiming that the equivalence principle relativizes motion to accelerations, which is not correct. Reissner correctly saw that there was something wrong there, but then he realizes that Einstein's equivalence principle has something valuable hidden in it. And he calls it the equivalence hypothesis, which I was very happy about, right? Okay. Which asserts the mechanical optical identity of an acceleration field with a field of constant gravity seems to imply the deeper meaning that gravity is also a resistance to acceleration. And then he goes on. If I'm successful, gravity would be understood as a direct and necessary consequence of the relativity of inertia, of acceleration. The identity of the gravitational and inertial masses would be shown to be self-evident, and the gravitational field would not only be equivalent to an accelerated space, but gravity itself would be identified as resistance to relative acceleration. Okay. So who was Hans Reissner? Very briefly, he was a pioneering German aeronautical engineer. He was, in fact, fun fact about him, the first person to build an all-metal aircraft, which is here, the Reissner Canal. And so if you took a plane to get here, or have ever taken a plane in your life, you can thank Hans Reissner, who was the first person to build a plane that had both, all metal means, not that the seats are made of metal, but that the wings and the body are both structurally made of metal. And he's the first to derive the Reissner-Nordstrom metric in 1916. So after this work on this Machian classical model, he goes on to join Einstein for a little while and derives the Reissner-Nordstrom metric. Nordstrom only does it like several years later, I think. So it should really be the Reissner metric. Okay. And then he also articulates Reissner's hypothesis, which is why we're interested in him today, in 1915, but he sends the paper to the publishers in 1914. Okay, so now that we've covered, how much time have we got?
You have 45 minutes left.
Okay, very good. Yeah, because this is going to be a bulky section. All right, so now that we've covered the motivation for these kinds of models, we're going to look at these different models, and special thanks to Dennis Brown for this section, who I'm basically going to be talking about our collaborative paper where we went through a bunch of these models over the course of the history, over the course of the 20th century. And we're going to look at different features of them, how they compare to one another, and what are some of the most interesting features that they have to offer, right? So here's a little chronology. It really stretches back, like it's quite well spread out, these models. And they almost all came up with their results completely independently of one another. And then later they would write papers saying, oh, well, 7 people discovered this before me. I didn't know at the time. And which is especially remarkable in some cases when the theory is almost always exactly the same, right? So I've categorized them so that in red we have Reissner's theory, Julian Barber's theory, and Richard Cook's theory, because they have some similarities, as we'll see. Then there are also similarities between the Schrödinger and the Cease theory and that of Trader, although it's slightly different for reasons that Dennis is particularly keen on. And then I've highlighted this in a different color. This is Sharma's theory, which is interesting for some other reasons that I'll talk about as well. Unfortunately, we don't discuss Guy Berninston Brown's theory, which is very little known about, from 1955. But it's also one of these models, kind of Machian models of gravity and inertia in the entire universe. Okay, so first of all, explaining gravity from relative inertia. So we're going to look at Reissner and Barber's models. We'll look at Cook's, which is related right at the end. So we have our classical mechanical Lagrangian. We had a complaint about this, that this refers to absolute velocities or velocities in absolute space. And so you're either, if you're going to take a Machian perspective, either you have to admit the existence, the physical reality of absolute space. But you might not want to do that because you might want to say that space is a conceptual and its homogeneity is a conceptual construction. Or you have to somehow relativize the quantities and replace and acknowledge that this is just an approximation in a roughly homogeneous universe, okay? So Reissner proposed an expression that looks like this. He sees that it satisfies his first postulate. Postulate 1, the inertial forces of mechanics can be represented as a resistance to translational acceleration of a mass relative to all of the other masses in space. Okay? Then he realizes that an additional attraction will arise provided that there is an additional hypothesis that your mass points are vibrating somehow, right? So he creates a theory of relative inertia, and then considering the hypothesis that his masses vibrate, he gets out of this weight or Newtonian gravitation can be represented as an inertial force arising from the rotation of mass particles relative to each other. So to see how this works, I'm not going to go through the derivation, I'll just show you the force law. So this is the force he gets out from two particles that are vibrating. And it looks a bit strange, right? It doesn't look quite like Newton's law of attraction, but you have a 1 over r squared relationship here. And so if you assume that these are, the wave number and frequency, so this is speed squared, right? And the mu's are like, they're the masses, they're the source masses, they're not the inertial masses. Okay. Sorry, this should be an F because I changed my notation last minute. So by identifying this force due to the vibration of the particles with gravity, he gets this following expression to make sure they fit for the gravitational constant, which looks quite strange, right? But note that this is done within the framework of instantaneous action at a distance. And I've explored tentatively whether modifications of this Lagrangian to account for the retarded action, that is the fact that it's only your past light cone acting on you, not the present plane of simultaneity, right? It may lead to a different result looking a bit more like this, okay? And you can ask me a bit more about that in Q&A if you'd like to. So in a remarkable coincidence, exactly 60 years after Reissner's paper, Julian Barber also publishes a pair of papers in 1974 and 1975, which almost exactly correspond to the papers from 60 years before, from 1914 and 1915. So yeah, this is one of many coincidences, like it being the 111th anniversary. Anyway. Don't worry, I'm not fully schizophrenic. I don't take all those coincidences too seriously. But okay, so Barber proposes that the rotation of the particles so what does he add to this theory? Well, he proposes, and this is, again, he hasn't even come across Reissner's theory at this point, proposes the rotation may occur at the velocity of speed of light, which was not really in the conceptual horizon of Reissner as an engineer in 1914. And the most obvious possibility that springs to mind, this is a quote from Barber, is that the rest mass energy of the particle is associated with an incessant internal motion at velocity c, all energy then being kinetic in origin, or alternatively with the Zitterbewegung of elementary particles, which also occurs at c. And he notes a connection, once you get this expression, you get an expression of this form, he notes a connection with Dirac's large number coincidences. Yes?
What was the prior motivation for hypothesizing that small bits of matter might be rotating at c?
So for example, the Zitterbewegung is something you get out of the Dirac equation that Schrödinger discussed.
Okay, yeah.
And then it's also, I don't know, it seems appealing, at least to me, to think that maybe what we call rest mass energy is really some kind of kinetic energy of things moving at the speed of light.
Yeah.
And that, it's not a very concrete idea, right?
Well, I have my own reasons for thinking that might be, that are independent.
But it's intuitively appealing, at least, right?
Which is also what I was shown, also had the same thing with the light speed.
Yeah. So I think a lot of people are coming to a similar idea there. So he also adds, the idea will therefore be a theory based on a generalization of the Lagrangian we saw, in which special relativity and quantum mechanics play an integral part, providing a natural framework for the necessary internal motion that would produce the gravitation. In such a theory, the four universals of nature, gravity, inertia, special relativity, and quantum mechanics, would clearly be linked in an intimate and inseparable manner. And I would also add cosmology, as we'll see at the end, because this relation has some implications for cosmology. And of course, Mach's principle is inherently related to cosmology. Okay, so that was the internal motion models, which explain gravity from relative inertia. Now, the models I'm going to look at now kind of generally go the other way around. So people want to modify gravity so that it's able to account for inertia in a physical way, right? But in some sense, it's the same thing, whether you think of it one way or the other. It might be a question of taste. Okay. But they do differ in that, as we'll see, there isn't quite the same degree of unification. So for this would be, okay, so the first person to suggest something along these lines is actually Emanuel Friedlander, straight after the passage that I showed you much earlier in the talk. Emanuel Friedlander adds a footnote where he adds, among other things, this little comment. For this would be very desirable to resolve the question of whether Weber's law applies to gravitation. And Weber's law is Weberian electromagnetism was, before Maxwell, a relational antecedent to Maxwell's theory, right? And okay, so 10 years after Reissner's paper, Schrödinger now in 1925 is the first to actually apply this, although he doesn't even refer to it as Weber's law, even though it's mathematically the same. And so he proposes this Lagrangian here, and it differs from the one we saw before because there's actually two separate terms now. And he's not considering any internal vibration. He's considering gravitation coming separately, right? So how is this a unification if you're keeping the two in separate terms? So yeah, so unlike the previous theories, they derive from separate terms in Lagrangian. Again, this one is the gravitational potential, Newton potential, and this is the inertial potential. This is only a unification if we should at least expect that the proportion between the two is fixed and should be around about on order unity by analogy with Weber's theory of electromagnetism. And so by fitting to the known perihelion shift, so this is an empirical fit, it's not an a priori result, Schrödinger does calculate the proportion as being the number 3. And then he's able to calculate the strength of the gravitational constant, which he gets g equals c squared over 2 phi, where phi is the sum of all of the masses divided by the distance. Okay, my text died. Okay, yeah. So in 1989, Andreas Sies independently rediscovers all of this and has since elaborated much further. He's also written a bunch of books looking at the history of Weberian electromagnetism and also has tons of really good citations for the history of these Machian models. So they're really worthwhile looking at Sies's books. Okay. And again, he derives exactly the same theory independently without knowing about Schrödinger's. Yes?
Phi is a sum of masses. Which masses?
All of the masses of the universe divided by the distance.
How did he know that number? How did he get that data?
No. So this is fitted so that inertia comes out right?
Okay.
So this is the Lagrangian for a pair of particles, but if you were to look at the Lagrangian for a single particle with respect to all of the other masses, you get a sum over all of the masses of the universe, and so each particle has its own little inertial influence. Okay?
Okay, that's pretty convincing of something.
Yeah. Okay, so that's where that's coming from. It's basically from this summation. So the models we've considered so far of Reissner, Schrödinger, Barbour, and Assis all lead to this tensorial or anisotropic expression for the inertial mass, which is experimentally refuted. Although in 1961, Dickey argued that this anisotropy effects may be unobservable due to covariance of measuring apparatus. This is the same kind of unobservability as you have like in Lorentzian ether theory, for example, where you can't observe the ether frame because of the covariance of your measurement apparatus. So that's been suggested as a way to get out of the anisotropy issue. But for those who reject Dickey's suggestion, Hans-Jürgen Schrader also proposed a slightly different modification, or a slight modification to this Lagrangian, which would avoid these issues in 1972. And so the essential difference here, the only difference, is that he's using relative velocities rather than the rate of change of the relative distance. And for some reason that I haven't actually looked into in detail, this gets rid of the anisotropy effect. And so in Schrader's theory, he uses the same as Assis and Schrödinger fit to the perihelion precession and calculates a value for this constant of 3/2, and then he gets this value for the gravitational constant. So although the inertial mass now is no longer anisotropic, Schrader's Lagrangian loses rotation invariance because, in fact, the relative velocities are not invariant under rotations of the system. And so you might think, actually, this totally undermines Mach's principle. And it kind of does, but there are ways to get around it by reintroducing another term in the Lagrangian, which would get rid of the rotation effect. So that's something else to look out for if you're looking at this kind of theory. Now, okay, so now I'm going to talk about Dennis Sciama's model and a suggestion of a link to special relativity and why it suggests this link. So first of all, so Sciama's theory is called On the Origin of Inertia. And it differs quite substantially from all of the others which work with like a Lagrangian and fairly complete theories on their own terms. Sciama's theory is not a complete theory. It was really just constructed as an illustrative model that he made over the course of his PhD studies in order to illustrate how he was thinking about applying Mach's principle in a new gravitational theory. And what he does, is it works with an analogy with Maxwell's electromagnetism. So these are the potentials for Maxwell's theory. And if you simply consider these densities as mass densities, then you get Sciama's model. So the model is invariant under linear accelerations, provided that this expression holds. And you can see that quite simply, because if you accelerate your entire universe, this will cause the rate of change of A to have a particular value, which then produces an acceleration on a body that's within this field, right? So it's a different kind of approach. He's not working with the Lagrangian, but it also kind of works. And similar to the models of Schrödinger, Assis, and Schrader, he uses two separate potentials, but the proportion in the coupling is fitted from two different means, right? So he's not going to fit the proportion in coupling by fitting things to the perihelion shift of Mercury. Instead, he has two separate other means, which are not actually explicitly discussed in his paper, but which imply something quite interesting, right? So firstly, the proportion in the Newtonian constant, the Newtonian coupling, and the inertial coupling is fitted by direct analogy with Maxwell's theory, right? So that they have the same coupling constant. Or they have like a proportion of c squared or something, right? But then secondly, on grounds of special relativity, rotation invariance is approximately achieved due to a modification of this field as long as the 4-vector making up the potential is interpreted as a 4-vector. So if this is a special relativistic 4-vector, we're going to be able to fit the coupling. And that enables this modification of the scalar part when you have a rotating frame, which looks like this. And this is a result from special relativity. Now there's a problem with this procedure, which is that this modification of the scalar potential, which is actually what's responsible for the Coriolis, sorry, not the Coriolis, the centrifugal force in Sharma's theory, and enables him to get approximate rotation invariance, is, how to say, it's not sourced in the masses of the universe. It's due to the background Minkowski spacetime that he's implicitly assuming here. Okay? So he hasn't actually satisfied Mach's principle in the way that I initially thought he had. However, what this all seems to imply is that if you had a theory of this kind of form, where under rotations the scalar potential would get appropriately modified, then you would get contact with special relativity and you would get a rotation invariance theory. And so I've tried to develop that recently. For now, I'll just say that there's an implication that we can make contact with special relativity through this. And so this is also interesting because it suggests that if such a theory would be developed properly, the contact with special relativity may lead specifically to this result, G equals C squared over phi, right? And we're going to see why this particular equation is interesting later on. Yes?
Can you explain in more detail what rotational invariance means in this context and what contact with SR means in this context?
Okay, so...
You could, of course, move on if you just don't have time for this. I've lost track a little bit, though.
All right, so the rotation invariance, I mean, this is the whole idea with these Machian theories, is that if you've defined inertia in a fully relational way, so when you were changing the Lagrangian in these other models and so on to define inertia relationally, then if you were to take the entire universe and in your mind imagine it rotated in space, nothing would change, exactly.
Yeah. Okay.
And so that's the rotation invariance you want. And the Lagrangian approaches are much simpler. It's much simpler to achieve this because you just directly make sure that your Lagrangian is rotation invariant, and then you know that your dynamics is also going to be rotation invariant. It's more difficult when you're kind of like bootstrapping it from Maxwell's equations, right? So, yeah. So that's that. And then the contact with special relativity, I mean, this is really because he's using a special relativistic result. So he's using the relativistic modification of 4 vectors, like the transformation properties of 4 vectors under rotations. Yeah, I mean, that he gets like the correct centrifugal force, at least for low velocities, from this procedure is, I mean, it's misleading in his paper because he doesn't discuss that it's actually coming from special relativity and they're not sourced in the masses. But it suggests that if the theory was modified correctly, somehow it might be able to achieve these results, right?
So about 20 minutes left.
Okay, yeah, okay, that's good. All right, so next, Cook's model and a link, possible link. So we've looked at a link to special relativity of these models. What about a link to quantum mechanics? So Cook writes this paper in 1976. This is literally, and it's the same topic as Julian Barber's paper from the previous year, and the same as like the 1915 paper of Hans Reissner. And it's published in the same journal as Julian Barber's paper of the previous year, and yet they didn't know about each other's work. And then Julian found out about Cook's paper some years later and puts a little footnote in his proceedings to the conference on Mach's principle from 1995. And then I had not heard about it at all until I found this footnote in that book. And then I contacted Cook, and he still didn't know about any of these people's theories. He didn't know about Julian's paper. He didn't know about Reissner's. He didn't know about, well, he knew about Sharma's book. He didn't even know about Sharma's 1953 paper. So there's been some lack of communication, right, over the course of and that's why people keep reinventing the wheel here, right? Okay, so in Cook's paper, he's not working with this Lagrangian approach. He's actually working from a result from Sharma's book from 1969, which is about the physical foundations of general relativity, where Sharma is kind of like making, well, he's talking about some things that he admires in Einstein's method, in going about deriving general relativity, and particularly puts emphasis on the equivalence principle and Mach's principle. And in this, he writes at some point this expression of like an induced, according to this Machian picture, you would get an induced, how do you call it? Induced inertial influence if a particle nearby is accelerated. So this is in order to gain acceleration invariance, invariance on the linear accelerations of your universe as a whole. You need a force law of this form, where here you're integrating over the matter density. This is the acceleration of the given matter that you're integrating over. And then these constants are there because it's interpreted as a force of gravitational origin, right? And this implicitly already assumes the formula G equals c squared over the sum without the acceleration here, okay? So this is in order to get acceleration invariance. So if the sources of inertial influences, so then he considers, okay, he then considers if the source of inertial influences is vibrating isotropically with some velocity v, there's going to be an additional force produced by this inertial force working from Sharma's vector potential theory, right? And it's important to note also that this model doesn't need the scalar potentials from Sharma's 4-vector theory. This is only working from the 3-vector potential for inertia. So he's not assuming the scalar potential which is responsible for gravitation. But he assumes that the masses which are responsible for relativizing inertia are also vibrating at some velocity. And this will produce an additional force, and I can sort of like visually explain why this happens. So if you have two particles like this, and this particle is accelerating in that direction, it will produce a very small acceleration in this particle over here, right? And if it's vibrating like this back and forth, then when it's over here, it's accelerating in this direction, which will produce a small acceleration in this particle this way. When it's over here, it's accelerating in this direction, which produces a small acceleration this way. But because it's slightly closer when it's over here and slightly further away when it's over here, the net acceleration is going to be in this direction. So you end up accelerating the particle. So that's actually really helpful because it also explains why we're getting the gravity out of Reissner and Barber's models, which we're working with the Lagrangian. It's the same mechanism, effectively. It's just visually easier in this kind of Sharma-Cook setup. Okay. So the time average force comes out as this, and it's related to the velocity squared of the vibrating particle. It's independent of the radius, by the way, because if the radius is smaller, the acceleration is greater. So even though the difference will be smaller, the acceleration will be greater. So yeah. So we have this time average force, where this is the time average, so this is the time average of the velocity. And then he's able to show that by identifying, rather than doing, using a classical model where he's not able to get the correct force to be consistent with Sharma's theory, which was implicitly using this result G equals c squared over phi. In order to get a force consistent with this, he actually has to use quantum mechanics because he needs this to correspond to Newton's law, right? And for that, you need your velocity squared to be 3 times the speed of light squared, right? Which is a weird result that you get your average velocity squared to be 3 times the speed of light squared, which is just a strange result you get in quantum mechanics. And the reason it's 3 times, as far as I understand it, is that in whatever direction you observe it, it's always the speed of light. And so if we're kind of assuming that it's statistically randomly going in all directions, and it has to be 3 times the speed of light, it's not really 3 times the speed of light. It's just, it's always moving at the speed of light, okay? So he uses this strange paradoxical result from the models of the Dirac electron and recovers Newton's law at the right size, right? So basically what this shows is that in some way you can take the inertial part of Sharma's theory and you can get out the scalar gravitational part. So when I was complaining about the fact that the two seem to be postulated independently of one another, you can potentially derive one from the other. But this, I mean, if you see where I'm going with this, you might see that this sort of implies quite a serious change of perspective of relativistic 4 vectors in general. This kind of result is going to apply more generally to 4 vector quantities and special relativity. Yeah.
It looks peculiar that Koch used the paradoxical result, the average of the V1 square is used 3 times of C2. Why is so fast? So did he give any justification to that?
I mean, have a look at Cook's paper for discussion of this. There's another derivation where you can kind of bypass this stuff and not start thinking of it. Like, it seems to me that the notion of the average velocity of the particle is a bit fishy, or the average square of the velocity is already a bit fishy, and so we shouldn't. So that's where the problem is coming from. But you can do the whole thing without actually referring to 3 times the speed of light squared. Yeah. But it seems to be a fairly solid result, especially, well, at least if you accept like the Zitterbewegung interpretation and so on. Yes, have you got a question?
Is it natural that in the river model you have a sink of coordinates of space for the outward coordinate of time? So you have inertia and gravity in the same package.
I'm not sure what you're saying exactly, but let's get back to it in Q&A maybe. Okay. So from this, so as I said already, Cook's implicitly using this result, G equals c squared over phi. And this sort of reveals potentially the harmony of this result with this quantum approach. So we already have the harmony with special relativity potentially, the harmony of the quantum mechanics. So yeah. So what's so great about this equation? So there's even more, right? Not only does it bring together Mach's principle, special relativity maybe, and quantum mechanics. In his 1953 paper, Sharma points out that this expression implies that the total energy, inertial plus gravitational, of a particle at rest in the universe is 0. So this is the energy of a particle at rest. We have the rest mass energy, m of the particle times c squared. And then its negative energy from being in the gravitational whirl of all of these masses is negative mp g phi. And if we take this relation seriously, we immediately see that this is zero, right? So every single mass of the universe in this model is contributing exactly zero energy to the universe, okay? Or in other words, the rest mass is perfectly compensated by the negative gravitational potential. You could remove all of the masses one by one and just have nothing left, and you have the same energy, you have energy conservation. Which sort of also implies that if we take energy conservation as a very general principle, this is kind of what you would expect in a theory of creating the universe, right? A theory that's capable of explaining the creation of things. And so this has actually come up in this context. So similar constraints on G were discussed for just this purpose, especially by Haas in 1936 and by Pascal Jordan especially in 1939 and in some other papers too. And these were totally independent of considerations of Mach's principle. They were connected to the Dirac large number coincidences, and they were also connected to some ideas that were around at the time quite popular about the continuous creation of matter. How could you have matter created and not violate the energy conservation principle? And so this was what they had in mind. I would say that it's also relevant to the creation of the cosmos as a whole, right? Even if it's all made at the Big Bang or whatever you want to say, it's still relevant to have this kind of relation. So in Sharma's theory, this result is somewhat mysterious, but more broadly, it's reminiscent of the necessarily zero total linear and angular momentum of the universe due to the relativity of motion in Machian theories. Again, I want to emphasize Haas and Jordan were not even referring to Mach's principle at this time. But in the context of Machian theories, you also have zero total linear and angular momentum of the universe because all these quantities are defined relationally. And to me, this suggests that if Barber and some other people are correct, that the rest energy of particles is really due to some kind of internal motion, that all energy, as Barber said, is kinetic in origin. Perhaps it's natural that the relativity of motion also gives rise to a zero energy universe as well as a zero angular momentum and zero linear momentum. Now, I can't exactly say with confidence why this is the case, but this sort of seems to be in harmony with these other ideas. How much time do you have?
6 minutes.
Okay, good. Yeah. We're near the end. Okay. So there's also apparently a link to the critical density condition in cosmology, which would give this result some empirical credence because there's a lot of experimental tests of that. So you can see in my recent paper, which is on the archive, it got rejected, so we have to write it again, which is a pain. But anyway. So this is from an interview of Dennis Sharma in 1978. Sometimes I've had a preference for the universe that just expands forever. So this is after his work on Mach's principle, much later in his career, where he's become slightly jaded about the whole concept. He was very keen when he was a young man. And then, but he still, as we'll see, hopes that this kind of result pans out. So I once hoped that, and that hope has not been realized in the work up to date, that Mach's principle would lead to the unique model of the universe. The Einstein-de Sitter model is the one where the total energy of the universe is zero, the kinetic energy and the negative gravitational potential just balancing. If you think that kinetic energy manifesting inertia is due to gravitation, then you might intuit that the most Machian way of having one made by the other would be if there's equal amounts of energy, which would give you uniquely the Einstein-de Sitter model. I have a secret hope that this might still turn out to be so. And it's a secret hope because at this point, experimental cosmology has shot off, and there's so much data around that people are much less keen to speculate and make, wild cosmological models and so on. because it's too much big data. Okay, and I'll also mention that Unikrishanan has also emphasized this connection to the critical density condition. He's written a book recently, Cosmic Relativity, making very similar points to what I've heard a few different people talk about today. That really the relativity theories, well, not relativity theories, what we need to be looking at is relativity with respect to the cosmos as a whole and so on. So he's worthwhile reading. So a summary of my talk. I started out with Mach's principle. I claim this is a critique of the classical notion of causality where single causes are identified as the cause of single effects. And for Mach, we need a cause of inertial motion. So inertial motion is not motion in the absence of causes. Mach's hypothesis was that inertial motion might be caused by the masses of the universe, that they might condition the inertial frame. And then Reissner's hypothesis was that relativized inertia relativized in this way, may directly give rise to gravity somehow. Then Reissner, Barber, and Cook derived gravity due to particle vibration. Schrödinger and Assis use Weber's potential. Schrader uses the Riemann potential, which is similar to the Weber potential but with relative velocities rather than the rate of change of relative distance, to avoid anisotropy. Sharma's model connects with special relativity, I claimed. Cook's model connects with quantum mechanics, as Barber had suggested the previous year. And then the resulting constraint, G phi equals c squared, also implies zero total energy and is associated with a critical density and seems to involve a conception of matter for which motion is fundamental. All this suggests, in my view, an exciting synthesis of special relativity, quantum mechanics, gravity, and cosmology. So, thank you. Oh, I go on. I also have like a bunch of references.
Good on you.
Okay, yeah.
I'll make a comment about how flowing space relates to this idea, and it's pretty simple because it gets rid of Newton's, solid space that holds on to everything, and, interacts with it accelerationally. So this massless frictionless space is flowing into matter everywhere. If you have a single mass, it will just cause, in a cosmos of space, it will just cause all the space to flow towards it. If you push it, it will have no inertia because there's no other mass pulling space or tethering space, giving it some kind of, ability to resist the acceleration of that mass. So that directly leads to the same concept that you need other masses to have inertia. It's got to be an interaction between masses and not just a single mass isolated in the cosmos.
Right, yeah, I think that's a good image or analogy, like to think of like, I mean, if you want to have like a field theory, like general relativity or like Sharma's theory or like a flowing space theory, to think of the masses as tethering space in some kind of way. Yeah, and so Mach's principle in that context would be that the space is fully tethered by the masses. It doesn't have its own independent inertia and so on. Yeah. Okay. Yes.
So this is a question for both you, Jonathan, and Chantal. This seems extremely fruitful, a lot of this, because it seems like it integrates completely, and maybe even what Donald's thinking about, but like this seems to integrate, this seems like it could integrate very strongly with a bunch of things you're already saying about how these particles are waves, that they constitute a rotational something of what the ether's doing, and then those rotations within the ether attract one another by affecting the ether at these locations. And I'm not it feels very connected is the best I can say right now. So
Vibration.
my question is, can you see what I'm seeing here?
Yeah,
Yeah.
I can see something. I don't understand all the details, I have to be honest, so I'll have to
Yeah.
probably read out more on it, on the details to understand all of it.
Yeah, there's a lot of this stuff.
Yeah.
This is a metric ton. But it
But I can
feels
see-
like it connects. to
So
what
let's
you're
keep the
doing.
questions for
Yeah.
Jonathan, please. Any other questions?
Alexander,
Yeah, first of all, it's really amazing your ability to distill the interesting stuff from this vast amount of literature. Really, congratulations for that.
thanks.
That's the first big point, and the second really minor. That's a little. You talked about energy conversation. I'm not sure about single particle or the cosmos in its entirety. Just a little caveat here, because we should keep in mind that energy as a concept was invented that because we wanted the laws of nature to be time independent, which is something we should not take for granted in the evolution of the cosmos. So there might well be a cosmological violation of energy conservation, just that, of course, we have to, maybe some other guiding principle, but that's nothing to do with.
So I do have a lot of views about this. I mean, one thing I would say is Mark's written a book about the conservation of energy, where he traces, and it's exactly this, he traces the principle of conservation of energy historically in many different derivations in different fields to the requirement for the impossibility of perpetual motion. And then he says at the end, this is related to the law of causality. And he's, we've talked a bit about the whole Hume-Berkeley thing and idealism. And I mean, he's a Kantian in some sense. And so he sees the law of causality as one a priori principle that we kind of have to assume in order to do science. And so the energy conservation principle just becomes an image of that. And he's actually writing this book in order to dispel the kind of like energy mysticism that was around at the time, that energy is this substance that's magical or something, you know. And so, so what I wanted to say, implicitly in Marx's thought, he's not even considering time asymmetry. So the whole Noether thing, the connection with Noether's theorem comes afterwards, because they're all assuming that your laws are going to be time symmetry invariant. I would say that this is also a kind of methodological presupposition. And I have some debates with some friends of mine about this. You know, can the laws of physics be evolving over time and so on? I would say, like, as long as they're evolving according to in a predictable, rational way, then there must be meta laws that describe how those laws are evolving. And those laws are going to recover the time symmetry, right? So when we're talking about laws, you know, just describing empirically what's happening in the laboratory, it might be that if you take big enough time scales, you lose the symmetry. But if you can find the law that's describing how that change is happening, then that law will be more universal and will recover the time symmetry invariance. And so just this kind of reasoning about energy conservation principles, symmetries, and so on, has led me down a path of defending Euclidean a priorism, or defending the concept of space and time and their homogeneity as a methodological tool rather than as a concrete physical reality. But yeah.
I mean, flat space, Euclidean.
Yeah. We'll get to the video someday.
Any further?
Can you talk about a little bit more about what Siama tended to go from vectors to tensors? Because he tried, right?
Yes, I mean, I haven't looked in a huge amount of detail, but he does this. So his PhD thesis, I think the third chapter, essentially makes it into this paper that he publishes with the simple vector model of gravity and inertia, where he derives all these nice results. And then in the following chapter, I mean, I think yeah, I'm not so sure exactly what he does again, but he changed his conceptual framework a bit, and he's no longer talking about rigid rotations of the universe, which I think kind of goes down into similar problems that Einstein came into. So
his thesis.
yeah, I can send
It's not
you.
available, so
I can send it to you if you
went
like.
looking
Yeah,
for it, right?
yeah. I got it from the Cambridge archives, and then I got it to get it digitalized.
All
and
right,
then
that would be nice.
yeah, I can share that with you. Yeah, no problem.
During one of these thinkers' derivations, there was an assumption about the mass distribution of the universe, and that assumption came from a Lagrangian that managed to get gravitation from inertia, right? Was that mass distribution ever confirmed by observations?
So
Because that would be really cool, right?
so are you thinking about like the models of Reissner, for example, or
I forget which. There were so many
I mean, yeah. There's
models, so many figures and models.
so this is Reissner's, right? And
Okay.
I think this is quite remarkable, right? Because he's working in 1915. This is way before any cosmology, and he winds up. I mean, it doesn't look as nice as Schrodinger's from 10 years later, but I mean, you can tidy it up, and you've got effectively a relation of the form g phi is approximately c squared if you take these k omegas to be velocity moving at the speed of light. And so if that's to be correct, this would imply that the universe is much, much bigger than was thought of at the time, right? I mean, even with any velocity, the universe is already huge according to this equation. He doesn't talk about this, but of course, cosmology doesn't seem to be on the way to like dismissing this. It seems to be exactly the other way around, on the way to showing that this result actually holds of the real world. Especially in the light of the fact that this fixes the critical density and the association between these Machian results and the critical density condition suggests that yes, that the actual distribution of matter does correspond to the one that would be needed for this kind of model to work. So yeah, I think it's very promising.
It's not proven, but we're getting there.
I mean, there's no way you could ever have like total accuracy with this kind of thing, like integrating over. But looking at
it's consistent with the observable universe, right?
Well, even that, no, I think there's you can never calculate these sums. You can't do these summations for the entire observable universe by hand or by computer. Or you need too many measurements and so on.
Okay.
But
Yeah.
if indeed it is related to the critical density, then we can just measure whether the universe is at the critical density, and then if it is, then that's a coincidence that lines up perfectly, right?
Yeah.
So
Yeah.
okay, yes, another question.
Yeah, maybe comment on that, how to calculate this. I mean, of course you had a lot of uncertainty, but as a matter of principle, you look at the Milky Way, you give an estimate of 10 to the 41 kilograms, and then you look out in the universe, you count the density of galaxies, and of course it's a mess because there are large voids, and is it isotropic or not? There are discussions, all sorts of discussions about that. But as an order of magnitude, you arrive there at the mass of the universe. It's something well defined, as I say, even if it's terribly difficult in the redshifts and luminosities, and the mass luminosity relation enters the game. So we have, unfortunately, it's not very precise, but we can't do that.
But it's within the bounds
Of course.
of current precision, is your point.
As a tendency, mass is missing, that's because they add all this dark matter stuff, but you don't see the gas, for example, the dust. It's invisible. So there's you don't see black holes if you believe in that. So as a tendency, the the visible
Yeah.
mass is always less than what you reasonably can assume, but more or less you can arrive there.
Okay. I'm seeing
It's a
why
reasonable
this would be
premise.
so hard to actually empirically calculate from observation.
So this equation is actually is quite similar if you look at it to the relationship, to the relationship you discover in Maxwell's theory. C squared is 1 over square root. C squared is 1 over epsilon 0 mu naught. Except that those numbers were already known to fairly good precision at the time, right? And they're much easier to experimentally confirm. So that confirmation experiment, of this coincidence, this calculation of these constants, led immediately to a confirmation of the theory. Whereas this, I think, is promising from various different ways, but it's so much more difficult to calculate.
Yeah.